gives me great pleasure to introduce you Dr. Tobias Geyer. Tobias got his Ph.D. from ETH under the supervision of Manfred Morari, and then moved to different positions in industry in the power electronics world, with stops at GE, corporate research in Munich, then the University of Auckland in New Zealand, and then later with ABB Research and now the ABB Motion. He combines a very deep scientific rigor in the control methods with what I would call hardcore industrial applications. And without further ado, Tobias, the floor is yours. Thank you very much.
Thanks a lot for the kind of introduction. Thanks for being here. Thanks for making this possible. For the conference organizers, it's a great pleasure and an honor to be here and to talk about my favorite topic today to you, which is control and computation of power conversion systems. Before we delve into the details, let's first maybe understand a little bit what a power converter is. So it's always about DC to AC, or AC to AC, or DC to DC power conversion. So you will have one waveform on one side and another waveform with a different voltage, different current, different frequency on the other side. And because it's high power, so you cannot use a linear amplifier, so you will always try to approximate sinusoidal waveforms using switching. You will always operate your semiconductor devices in the on-off mode, not in the linear mode. So it's intrinsically a switched linear or nonlinear system. And that, at least from a control point of view, makes it very interesting, if not to say challenging. Now, this little building block you see there in blue, that's omnipresent. I mean, we have it everywhere around us. And if you take a power system specific view and maybe you start at the high voltage, you see here the high voltage or the ultra high voltage grid. Prominent examples would be high voltage DC power conversion. So you go from AC to DC, alternating current to direct currents, back to alternating currents, to have long range power transmission. So these systems would be in the gigawatt range. And then if you take a step down, you end up with medium voltage, with megawatts. Medium voltage being between 1 kilovolt and 35 kilovolt. And prominent examples are offshore wind, are typical industrial applications called rolling mills, metals, large pumps, mine hoists, but also transportation. So if you are on a ferry or a cruise ship, I mean, at least with a cruise ship, you will always have a diesel electric or LNG electric propulsion system. So they're all electric propulsion. And then one level down, you end up with sort of medium to lower power in the kilowatt range. And here we are very familiar with transportation. Think of electric cars, electric car chargers, but also maybe smaller photovoltaic systems or maybe conveyor belts, maybe automation and so on. And that's sort of, yeah, and then you take one step further down and you end up in the watt range. So the low power, think of LED lighting, think of your phone charger, and so on. And maybe as a little disclaimer, I'm mostly interested in several tens of kilowatt and above. So I'm not going to talk much about the lower power end. So why would we look into control and computation for such power conversion systems? The vision is clear, I would say. It's really to get the most out of it. So to maximize the power they can deliver, their efficiency, their availability. We don't want things to fail and not be available. Interoperability, so that we can combine different converters together and they play nicely together. And this is being done by using computation, so numerical, mathematical optimization, as well as control. And the ultimate aim, because it's medium to high power, is to help decarbonize the planet. And I will have a slide about that at the very end. So, having introduced a little bit power electronics, I want to show you what control and modulation looks like for these systems, and then present you let's say, an academic view. That's the academic view from the power electronics community, with some challenges at the end, and then the industrial perspective. So what, at least I feel, is relevant for industry, what we are working on, along with challenges. And maybe some of these challenges might inspire you to look into them. Maybe these are problems there are already some solutions for, or one could develop solutions for together. So control and modulation, in the simplest case, you can think of a single phase setup. You would have on the left-hand side a switched voltage form. So you would have a power converter that gives you discrete output voltages, integers, let's say 0, 1, and -1. And you would have a load. And in the simplest case, it's simply a voltage with some inductance. And that might look like a trivial problem, but it actually represents the vast majority of applications we have. You can think of this as being the grid, the grid voltage, and L could be the transformers and the line inductances. And R, the ohmic resistance, is typically very small or even negligible. Similarly, you can represent a machine in a very simplistic way like that. So the task is almost always to drive a current, a sinusoidal current with a certain fundamental waveform, so a period of, let's say, 20 milliseconds, so that would be 50 hertz. And by doing that, you would try to manipulate the average voltage you apply. Now, this controller typically would assume you have a linear system, but then you would need some modulator. You would need to translate these voltage references, which are real valued, into discrete switching. And maybe the easiest way to do so is to introduce so-called carriers, carrier signals. And because we have here 3 levels, we would have 3 carriers. And whenever there's an intersection between your reference, the voltage you want to achieve, and your carrier signal, you will have a switching transition. You will switch up and down. And the beauty is, if you then sample at the right instances of time, so if you sample at the peaks and the bottoms of those carriers, you can show that the current ripple that you sample is effectively 0. So the controller will not really see that it's operating a switched linear system. The controller is can be ignorant to the fact that you have a switching power converter, and hence usually linear controllers are designed. Now, this also then masks the switching and limits the performance of the controller, because you end up with a delay, and the controller cannot directly influence the switching, so the switching is typically somehow ad hoc. And switching is always expensive. You always have losses whenever you switch. And this very simplistic way, you pay a significant price to get the simplicity. So the challenges are, when you now look at a 3-phase converter having just 3 phases, not just 1 phase, and having switching devices that allow you to achieve a plus, a 0, and a minus, but the same load. Sampling frequencies are typically in the kilohertz range, maybe in the high kilohertz range, let's say 50 to 200, 500 kilohertz. So whatever you want to compute, you have just 1, 2, 3, 4, 5 microseconds available, because you also need to allow for time to take the measurements and to send them back. The system is clearly an integer linear or integer nonlinear system, because the converter switch positions are your manipulated variable. So you have to decide on these switching transitions. And whatever in whatever way you switch and modulate, you will always introduce harmonics. And these harmonics have detriment effects. They tend to warm up your load, they create losses, and they might disturb control loops of other systems. So whatever we do, we need to make sure that these harmonics are limited to certain values. But we also then immediately see that whatever is done over this fundamental period of, let's say, 20 milliseconds, it is repetitive. So every 20 milliseconds, everything more or less repeats. And that presents an opportunity to maybe pre-compute switching policies that are optimal in one or another way, optimal, let's say, in terms of harmonic distortions, and to then design controllers that take advantage of these pre-computed policies, rather than just switching ad hoc and doing in every cycle things that are different from the previous cycle. So let's jump to the academic view. Let's start with a generic system, linear state space system. Pick a certain number of state variables. It's real valued. It could be such a converter system where you have an LC filter connected to a machine. So you have 8 state variables. We typically work in orthogonal coordinates, so we don't work in ABC in the 3 phases, but we transform it into a system that the quantities are linearly independent. And an example could look like this. You have the switching waveform in phase A, B, and C, the current, and then the filtered current, which is almost sinusoidal. Now, this is a trivial system, except for the constraints on your manipulated variable. So this is going to be an integer, and in this case, it's an integer with 3 values, -1, 0, and 1, and you have 3 phases. So you have to decide on those 3 switch positions. And typically, you're not allowed to switch by more than one step up or down. So hence you have this infinity constraint. Now in terms of objective function, in the simplest case, you just penalize the tracking error. You may want to track these quantities on the right-hand side, the different currents and maybe the voltage. And you will penalize them accordingly over a finite horizon, n. And you also have to penalize your control effort, your switching effort. So that's a way to limit or sort of keep at bay your switching frequency. And a trivial way is to add a weight, but a weight is a bit awkward because you have this trade-off and you have a conflicting trade-off. And maybe a nicer way is to introduce the switching frequency as a state variable, where you filter the past switchings and you predict the switching frequency over your horizon and you then track it, or you add a soft constraint on your switching frequency. And then you effectively avoid this sort of tuning in order to get your desired switching frequency. Now, if we take this problem and we reformulate it as an optimization problem, you immediately end up with the standard, well-known quadratic form, where this capital U is your sequence of manipulated variables over your horizon. In this case, it's a switching sequence. It's an integer manipulated variable. The complicating fact is it is an integer optimization problem. Now you can show that the Hessian is symmetric and positive definite, provided that the penalty on switching is positive. And that then allows you to decompose the Hessian into a matrix V, where V transpose V is equal to the Hessian using the Cholesky decomposition. And this matrix is unique, it is invertible, and it is lower triangular. So thanks to that, we can rewrite this quadratic form by completing the squares into the very compact form shown up here. So we have still the decision variable, our sequence of manipulated variables, but we now also have an unconstrained solution. And the unconstrained solution simply arises from neglecting the switching, assuming you can apply any decision variable, so you make it real valued. If you then minimize it, then the unconstrained solution would be the optimal solution. So what we try to do here is we need to minimize the Euclidean distance between the decision variable and the unconstrained solution in the space generated by the so-called generator matrix, this matrix V. And in a pictorial way, that could look like this. You have on the left-hand side your original space you're working in, your coordinate system. So that could be your phase A, that could be phase B. Phase C would be poking out at time step 1, and then this gets multi-dimensional for higher prediction horizons. We have 3 levels, so -1, 0, and 1. And if you take this generator matrix, you end up with this distorted space. So it's a lattice, it's a truncated lattice, and you have to minimize the distance between the unconstrained solution and the integer point in this distorted lattice. And that means if you have a integer point, let's say you have an educated guess, or you use the unconstrained solution and you round it, then you only need to look at integers within that sphere, within that ball centered around the unconstrained solution. And there is a nice branch and bound method that exactly solves that problem. It comes from the field of communication theory. It's called sphere decoding. So you try to find the optimal integer solution that is within that sphere. And because this lattice typically is almost orthogonal, it is very efficient to solve this integer optimization problem with that algorithm. So we do branching over the switch positions in the phases A, B, and C, so -1, 0, and 1. And we can only consider solutions within the sphere, so we do bounding. And we will do a depth-first approach, and then we can tighten the sphere. And this is a real example. This is actually a fairly bad example. So typically, you just need to traverse the minimum number of nodes to find your optimal solution and to find a certificate for your optimal solution. Now you can push that maybe a bit to the extreme. So this is an example where you have a horizon of 40. So you have 25 microsecond sampling interval, you have a prediction and control horizon of 40 steps. So we're looking 1 millisecond ahead. You see here the currents in the orthogonal coordinate system we're trying to track. You see the torque that results from the currents, and you have the switch positions down here. So things with negative times are the past, and everything to the right is a prediction. And you see that this works nicely. It is a non-convex optimization problem, hence the switching policy will have jumps every now and then, but the receding horizon policy works very nicely. Now, when you think about the complexity of solving that numerically, you have 3 to the power of 120 integer combinations, so, or 27 to the power of 40. And that's equal to 10 to the power of 53, and that's effectively the atoms in the sun. So you have an extremely hopeless problem to solve, but you can solve it because this lattice is almost orthogonal, and because the sphere decoder works really well for it. Now challenges would be, at least looking at this academic example, challenges would be, can we extend that? Can we add state constraints? Can we translate state constraints and still come up with an efficient way to solve the integer optimization problem? Or what would it look like when we have a nonlinear system model? What would be, could we come up with tight upper and lower bounds to use a similar method? Or should we rather use a short horizon and with a suitable terminal weight? But the terminal weight is a bit awkward because you will always have to do switching. So you will never converge to a steady state solution. You can never drive your states towards 0. You will always have to switch. So you have to do some approximate dynamic programming and so on. A second complication is the harmonic spectrum. So when you take your variables you're interested in, like your currents or your voltages, and you compute the harmonic spectrum, then you will see that it's flat. It's almost like white noise. And that's actually bad, because when you're connected to the grid, you have a grid-connected converter. There's certain restrictions in place, in particular restrictions in place for the so-called even order harmonics. So harmonics that are an even multiple of your fundamental frequency. You can try to shape your harmonic spectrum. You can add Fourier coefficients, and you can use the evolution of the Fourier coefficients in your system model, and you can then try to penalize them or weight them accordingly, like shown down here. But you pay a price. Your switching frequency goes up tremendously. So doing that without pushing up the switching frequency is a I would think, not yet solved problem. But the real issue maybe is that the switching with these sort of methods is non-deterministic. It is non-repetitive. So whatever you do in one cycle, you don't repeat it in the next cycle. So you see that what is done in phase A, B, and C bears no similarity. You would expect a phase shift by 120 degrees, but that's not the case here. And hence you end up with this white noise harmonic spectrum, and hence you end up with this sort of erratic, ad hoc switching ripple on your currents. So you're not making good use of your power converter. You're not pushing its capability to the limit because it's not repetitive, it's not deterministic. You can't predict it a priori what the performance will be. So the utilization is rather poor, and that means you need to add a significant margin, because when you sell a converter, you effectively make a promise to your customer that the converter will be able to do certain things, achieve certain powers, certain currents. And if you want to achieve that under all circumstances, you might have to add a significant margin. You have to, you might have to oversize your converter so that it at least achieves what you have promised. So I believe this is the main disadvantage of this method, and maybe also the main challenge. So let's then switch to the, let's say, industrial perspective. And it is all about getting the most out of your converter hardware. So you want to maximize the capability, the efficiency, availability, and the ability of different converters to operate together. And you can think of it like at steady state operation, where things are repetitive over 20 milliseconds. You want to minimize the ripple, the harmonics, or you want to shape them, and you want to get the highest current out that you possibly can. And you want to have a certificate that you have maximized it. During transients, you want to avoid trips. You want to avoid that you move your system outside of the safe operating area, that states or outputs start violating constraints. So here it's not about performance, it is more about survival. It's more about staying within bounds so that you don't damage anything, and so that the protection mechanism doesn't have to kick in. And the third one I will only discuss very briefly is interoperability. But let's start and look at steady state operation. And let's look at what people call optimized pulse patterns. So this is a way of computing offline your optimal steady state switching policy, switching solution. So just consider 2p fundamental period. You may want to approximate a voltage that is sinusoidal. It has a certain amplitude and a certain frequency. And we have a certain number of switching transitions available, a certain switching budget. So this will later determine our switching frequency. Typically, people assume some symmetry. And then the beauty is, obviously, you can compute a Fourier series, and the Fourier coefficients are effectively the amplitudes of the harmonics you will get. And in this case, the Fourier series and the harmonic spectrum would look like this. You will have harmonics at these typical 5th, 7th, 11th, 13th integers. And you then know your load, and these voltage harmonics get translated into load harmonics. So you can very easily formulate an optimization problem where you minimize the weighted harmonic spectrum. And you want to minimize it such that you get your desired voltage, so your desired fundamental component, and you want to ensure that one switching transition happens after another one. And you can see immediately this is not a nice problem to be solved. It's highly non-convex. You have these cosine terms in your cost function. You have it also in your equality constraint. If you have a small degree of angles you have to optimize over, you can do it very efficiently. But if you have dozens or hundreds, it becomes highly challenging. But given that you have solved this problem, all you need to do is you need to integrate it up. The integral of the voltage is the flux, though this is what you would apply to your machine. And because the switching waveform is optimal, also the integral of the waveform is optimal. And you want to follow this flux trajectory. So you would have a machine that has a certain flux at its inputs, its state of flux, and you want to force it along this optimal trajectory while using that pre-computed switching policy. Now the trouble is, you cannot manipulate the instantaneous voltage. You cannot say, I want a little bit more voltage, a little bit less voltage. So you can't just easily drive your stator flux error to 0 onto the trajectory. You can only manipulate the switching instances. You can only change the time when you switch. So you can do pulse width modulation, but you cannot do amplitude modulation. So you have to content yourself that it might take a little bit of time till you move back onto the trajectory. So this makes it a bit challenging. And maybe the simplest way is to say I have this error and I want to minimize this error over a certain prediction horizon. And whenever I have a switching transition coming up in any of the phases, so only one is shown here, whenever a switching transition comes up, I can manipulate it. I can switch earlier or later, and by doing that I can reduce that error so that at the end of the horizon I have close to 0 error. And the prediction model is trivial. It's two integrators in two orthogonal axes. So all you need to do is you have an error now, you want this error to be close to 0 at the end, and then you have a linear combination of your switching time modification weighted with the sign of the switching transition, transformed from the 3 phases into this stationary orthogonal coordinate system you see here. And this you want to minimize. So this is a quantity you penalize in your quadratic cost function. You will also have a penalty on the amount by which you change your switching. And you need to make sure that one switching transition comes after another one, so you end up with this quadratic program. The decision variable is the switching time modifications, and you can use an active set method, maybe a fast gradient method to solve this. You can also simplify it by using a deadbeat method. Whatever you do, you should aim for a computation time in the range of microseconds. So if it takes you 50 microseconds or 100 microseconds, this will be way too slow. Now, if you are really restricted and you're in a big transient, you might cheat. You might insert a switching transition that is suitable to you. You can insert pulses, but this is only to be used in rare cases. And they're very nice generalizations. So this is the very simplistic way. You can also introduce Dirac impulses. So you can say, I don't want to minimize effectively having here a terminal weight that you minimize. I want to also regulate it along its trajectory along the prediction horizon. And if you introduce Dirac pulses, sort of linearize the switching instant modifications, you can have a quadratic cost function where you integrate up the error over the horizon. And if you have a linear system, then you still end up with a quadratic program. So this is a very nice approach. References are not down here. But this is then suitable if you have a more complicated system, not just a trivial integrator. So this works very nicely in the lab, in the medium voltage lab. So you see here the state of the art, certain switching frequencies, certain harmonic distortions, which are reasonable. They're not particularly high, but using that predictive method based on pre-computed switching policies, you can reduce the switching frequency a little bit, and you can really significantly reduce that ripple. And by doing that, you can reduce the losses in your machine. Now, this works also dynamically, so you get a very, very high bandwidth because you manipulate the switching directly. So you get the same superior, very fast step during transients as with the established method. Now there are a few challenges. One is current distortions are not that relevant. What is much more relevant is that you get the most out of your converter. You want to maximize its power. So we will quickly look into that. What happens if you not just have an optimized pulse pattern with a few angles or a decision variable just with 5 or 10 entries, but maybe 100 or 1,000? And what do you do if online the situation you thought you had offline is very different? So how can you then adapt it? Is it then still a good method? So let's start with this power maximization. The main quantity in a converter is the semiconductor, the switching semiconductor. That has maybe 50% of the cost. So that is the quantity we want to focus on and make best use of. So if you assume you have a certain switching pattern, then you can maybe assume that you have a certain impedance of your load. And given that impedance, you can compute analytically what the currents and the voltages in your system are going to look like. And based on those, you can use loss models of the semiconductors to predict what the so-called conduction and the switching losses are going to be like. So here the device is on, and the current goes up, so the conduction losses go up. And down here you have switchings. Here you have particularly off transitions that are very expensive. And then we have water-cooled heat sinks. So the semiconductor is here in the middle, the heat sinks on either end. And the heat is produced in the middle of the semiconductor and then dissipated towards the heat sinks. So using a experimentally verified model, a Foster model of these heat transfer equations, you can predict what the steady state temperature is going to look like. Now this temperature, because you can model it, and if you can compute the gradients of how the temperature, the peak temperature changes as you change your decision variable, your switching angles, you can try to bound it, you can try to minimize it, or you can try to push up that current so that still your junction temperature stays below an upper limit. If it gets too hot, you will damage or even destroy your semiconductor. And similarly, you can do it for the other components you have, but this is much easier. The junction temperature is the hardest bit. And then you end up with a huge optimization problem. So you would pick all your different voltages you want to synthesize, all your different switching frequencies, and then you would say, I want to get the most current out of it, because current is power. Your voltage is given, but if you can push up the current, you will get out more power. You want to push up that current while ensuring that your components, that your models stay within their safe operating area, stay within their specified limits, and that can be regarding losses, power losses, temperatures, voltages, currents, and so on, while making sure your harmonic distortions are reasonable, are not excessive, and you get the desired voltage. Maybe there are a few more constraints, and you might do this over a certain set. You don't want to do that just for one operating point, but for a certain set. And this is a challenging problem. You have typically 100 plus decision variables. You have strong non-linearities. So solving that is a pain, even with a sophisticated optimization tool, even using a cluster. So the holy grail here is sort of, can you come up with good upper and lower bounds on your solution, on your value function? Can you come up with bounds that are meaningful and give you a certificate that you have achieved a close to optimal solution within certain bounds, let's say 5%, rather than just throwing initial conditions at your problem and solving it on a cluster for many days and hoping sort of for the best. And the benefits of doing that is you get a double-digit power increase of your converter. So if you used to have a converter that was able to achieve 10 megawatt, you can now get maybe 12 megawatt, the same hardware. And you can imagine that this 20% boost significantly increases your margin and makes you significantly more competitive. But what happens if you go to lower powers or higher switching frequencies? So this would be maybe the typical 100 kilowatt converter. So also there are huge performance benefits, huge improvements you can achieve. But how about you push it to the maximum? What is the infinite switching frequency? What's that going to look like? And it appears that even at infinite decision variables, you still get a very meaningful improvement. So this is just single phase, it's not three phase, but for three phase, it looks very similar. You might not need it for the megahertz range, but you need it when you are at standstill. At standstill, you have an infinite ratio between the switching frequency and your fundamental frequency. The trouble is, this is all based on assumptions. And the assumption is that your load is sinusoidal with some inductance, maybe some little ohmic resistance. But what about if your load is not sinusoidal, if you're connected to a grid, to the so-called point of common coupling, and if there are other converters, other players, other entities that inject disturbances into this point of common coupling. These we can, if they're not accounted for, they will lead to a large current ripple because you apply here a voltage that assumes that the load is sinusoidal. So any harmonics you have in the load that you are not mimicking, that you're not adapting to, will lead to a significant increase in the current distortions. So what you can do is you can rely on control, on feedback, but maybe you can also try to learn, try to adapt, try to modify on the fly. And the reason why you can do that is because things are repetitive. Every 20 milliseconds, the situation will repeat itself, and these disturbances, they will change only very slowly, typically. And one way of doing it is to estimate these grid harmonics. So there are different harmonic orders, different amplitudes, different phases, and then to modify your existing switching pattern or to maybe even compute a new one. And these are results from Sydney, from Elis Tsouras and his supervisor Ricardo. And what you see on the right-hand side in the beginning, you see a perfect sinusoidal grid. You see the harmonic spectrum down here, it's flat, there's just a fundamental component. You see the switching pattern that is optimal for the sinusoidal pattern, and you see the converter current, which has been, the pattern has been designed so that the low order harmonics are all removed. So this is desired. But what happens then is that harmonic distortions kick in. You now have harmonics in the voltage here, and then your switching pattern is no longer optimal. The harmonic distortions double. And this is now slowed down by a factor of 10 with around 200 to 300 milliseconds. These harmonics are estimated, and the OPP is recomputed with the new situation in mind. And again, you have perfect removal of these low order harmonics. And I believe this can be done for a wide range of cases, and there are other methods that might work even faster and might be even more suitable. Another major topic are transients, disturbances, faults. Maybe we need control in these cases, not at steady state. At steady state, everything is easy. We can pre-compute. We just follow a reference trajectory. But the imposition of constraints, of making sure we survive transients, this is maybe even more interesting than just operating at steady state. And one, I would say, fairly nice example is a truly high power converter. This one here is at 48 megawatt, where you have the line side here with a transformer. You have this rectifier stage with certain firing angles when we can turn it on, and it self-commutates and turns itself off. You have a DC link in the middle, and then the inverter. These converters are used to drive large compressors. And the control objective is very simple. Just achieve the desired torque, track the current in your DC link, and don't trip. Don't get too high a current here. Make sure the switching angles stay within bounds. If you start switching too late, you get these so-called commutation failures. So effectively, you try to turn it on when you can't turn it off anymore. So you need to avoid that, so you have these constraints. Maybe the constraint on the state, on the current could be a soft constraint. You have a almost trivial model. Trivial in the sense it is as simple as it can be while still being descriptive. So the current depends on the voltages you apply at both ends. You have some machine equations, and you have a nonlinear output equation for your torque. And this directly leads to a nonlinear optimization problem you can solve with a sequential quadratic programming solver. And you have reasonable time. You have almost a millisecond available. You have a millisecond sampling interval. And on the right-hand side, or in the middle, you see a measurement from the field, from Norway. You have here the grid voltage, which dips to below 40% for 80 milliseconds or so, and then recovers due to ice and strong winds in winter. And the torque of these compressor drives then also dips, but then recovers. And this is great, because previously, just using linear control loops, when you go below a certain voltage level of your input, you would not be able to achieve the torque. Your compressor would stall, and you would trip. And every hour of lost production in these big gas injection stations can easily cost you $500,000 just in lost revenue. And it often takes several hours to ramp them up. So such an event would cost the customer many millions just in lost export revenues. So what you get is you get an improved low voltage ride through, so you have higher availability. But what you can also do is you can operate your manipulated variables closer to their limits, to their bounds. So that means you get a higher efficiency. So this main downside of this type of converter is that it has a very high reactive power demand and not that good an efficiency when you're operating at these points. Now maybe an even more interesting problem is the so-called modular multi-level converter. So you have these little modules, they're all stacked in series to go to high voltage, to tens or hundreds of kilovolt, and that is state of the art for high voltage DC. And this is a fairly challenging nonlinear optimization problem. You need to control the currents, you need to control the individual voltages, you need to make sure you stay within the safe operating area. You have very fast transients, you have faults, and you have a humongous system that can easily cost 200–300 million. So doing sophisticated control is certainly worth it, even if you just improve it by fractions of a percentage point. The last topic I wanted to talk about is our converter-dominated systems. And one fairly prominent example is the first offshore wind farm that was connected to a high voltage DC link to the grid. So you have here on the right-hand side, you have groups of wind turbines. You always have 20. They're so-called doubly fed induction generators, each at 5 megawatt. Then you have a collector grid, a transformer. So this would be at 33 kilovolt and then going up to 155 kilovolt. And then here you have the point of common coupling offshore, and then the HVDC link that is translating AC into DC. Now the converter is here. You have some filters. And what happened in 2013, as more and more of these wind turbines were commissioned, there were harmonic distortions at the point of common coupling. So these are in the range of 20% voltage THD. And this is a 155 kilovolt bus. And you can imagine that these harmonic distortions were also visible in the filter. And they led to failures. I mean, there were even fires in these filter banks. And that was in the news. I mean, there were a lot of articles. I now have here only German ones. But the whole offshore wind turbine vision came to a halt because people weren't sure how to transfer the power from offshore wind to the onshore grid. So that led to a delay of probably several years of the development of offshore wind. Now a careful and actually not that difficult an analysis showed that there are resonances in the system. So I'm deliberately not showing you the frequencies down here, but they are in the range of hundreds of hertz. And I'm also not showing you the gains, but the gain is from a wind turbine voltage harmonic to one of the currents here in the filter bank. And these resonances are extremely sharp and will lead to a 10 times overload of the components. So a poorly damped harmonic. And why is it poorly damped? Because it's medium and high voltage. I mean, that's the very point of going to high voltages, that you don't have any resistances in your system anymore. So you need to actively dampen these harmonics. And the biggest player here is the HVDC converter station. So the HVDC converter station is by far the strongest one, and hence we added this damping loop to the HVDC converter and to remove these the resonances, to keep them at bay. And since then this has worked very nicely, and offshore wind has become a success story. And nowadays we understand that very well. I mean, at the time, people have probably not thought about these phenomena. People have assumed that the HVDC converter is connected to a fairly stiff grid, and vice versa. The wind turbines, I know for sure, have only been tested onshore, assuming they are connected to a stiff grid. So this interaction had not been most likely considered. Similar issues you can potentially have not just in wind farms, but also in any offshore isolated microgrids. Think of various loads, various generators that are now augmented by power converters. You can have it in DC grids on vessels or Navy, or on any remote site that is connected via a very weak link to the main grid and has lots of loads and lots of generating capacity online. And maybe what is the hardest here is protection. So whenever you have a fault, you need to make sure that you identify the fault and open the appropriate circuit breaker. And power converters are not suitable for high overload. They're not made for that. So you can overload them only for a few, maybe milliseconds, but maybe for not long enough. So here they have a shortcoming. So we should probably think about better ways to do protection. And the second challenge are transients. And transients by turning equipment on and off. So you constantly disturb your system. You constantly have huge inrush currents, huge dips in frequencies and power. You clearly have the topics of grid forming, grid supporting, various mode changes, but here I believe they are on a higher level of understanding than the first two topics. And one interesting one is passivity. So a converter should not react to harmonics it sees, it should ignore them. And in order to get passivity, you probably want to have as high a bandwidth as possible. So you want to not have a negative phase when you pick up that harmonic, because then you start amplifying it. If your phase is close to zero, you will not amplify it, you would rather ignore it. So passivity you can typically achieve by having ultimate bandwidth. So with that, I would like to slowly come to an end. Start with the conclusions. So the point of computational control, I would say, is to maximize the capability of your assets, of your power conversion system. Benefits are fourfold. You can get more power out of them. So you reduce the cost, you get a higher power density. You can make your system more efficient. So efficiency is becoming ever more important. So even just increasing efficiency from 98 to 98.2%, if you have a large installed fleet, can easily be the power that 100,000 households consume. So efficiency is more and more important, not just because it provides a monetary benefit, but also because it's driven by politicians. Then you want availability. So you don't want to have trips, you don't want to have any outages, so you want to survive them as well as possible. And many of them you can actually survive, a few you probably have to shut down your system. And you want to have this plug and play, this interoperability of converters, when they're all connected together, that they nicely play together and don't excite each other, don't lead to resonances. Now, when it comes to the productization of control methods, this is extremely time-consuming. And what makes it so time-consuming is because you have to build up know-how. You have to educate people. You have to transfer knowledge. You maybe have to hire new people with the proper skill set. So it's not a matter of a year. It's maybe a matter of 10, 15 years. So you need to have a very long horizon, a very long breadth in order to achieve this. And in order to facilitate that, a method should be as simple as possible. So any difficulty, any complexity, anything that might look mathematically very intriguing, unless it's really absolutely needed, is maybe not the best way forward. So simplicity is beautiful in order to aid productization. And whatever one does, if you are a big entity, a big company, you must not just focus on one application. You must not just focus on one product. You want to use the same method, the same concept for everything. You want one thing to rule them all. So it needs to be applicable to all the very diverse applications and your whole portfolio. So if you have one method that excels in one corner point of your portfolio, that's probably not going to fly. You need to have a method that excels everywhere. And you need to convince people that it will excel throughout the whole range. And I think what we also forget is we always look at the success stories, but we forget about the failures. And maybe here I show you 2 success stories, but I've not shown you 7 or 8 failures. So they are also there. And maybe they are even more interesting because you can learn from them. In order to get things into a product, to get things into industry, you need to almost prove a certain monetary benefit. Just performance without being translated into dollars or euros is not that compelling. It's not that convincing a story. So in just having a better performance, having lower harmonic distortions, having faster transients, if you can't map that into how this will make your product more competitive or less costly, or you can increase the power, this is not going to work. And one dimension to get things done is to get more out of your assets, to get more out of your hardware. And for this, control really is a potential differentiator where industry can differentiate itself from its competitors by having maybe similar hardware, the same components, but with the better control, you can get more out of it, and you can sell it at a more competitive price, or you can add extra features, extra capabilities that others don't have. And because of that, this whole story of model predictive control and power conversion control has been rising exponentially, at least in terms of IEEE publications over the last few years. So ultimately, the whole reason we are doing that is to make the high power converters more competitive and in a way to, if you want, to decarbonize the world, to help save the climate. So high power electronics has never been as exciting as today. You have a double-digit growth, so it's really going through the roof. You have a lot of new applications that previously didn't exist or people didn't think about. Some are actually science fiction applications. So you read IEEE Spectrum, and then salesperson calls me, and then I realize that this application he's talking about under an NDA is actually what you read in IEEE Spectrum, which is clearly science fiction by some startup that you think is absolutely breathtaking. You have a lot of challenging research problems, and you need these high power converters to save the climate, to decarbonize the world. So that means renewable power generation, so photovoltaics, wind, maybe hydroelectric power plants. You need to transmit that power, so you need high voltage DC. Maybe you also want to use hydrogen for that. You need to store power, so you have hydrogen, battery energy storage, you have pumped hydro. And then the electrification business, that's we are all aware of. But this is now moving towards vessels. So vessels are also being electrified. Maybe they also get a battery. Maybe they move to a medium voltage DC grid. And the same with planes. It sounds a bit like far-fetched, but small planes are already electric. Small training planes and these vertical takeoff and landing planes, they run electric, simply because there's no maintenance. So it is cheaper to go electric. And what is maybe sometimes overlooked is industry is as carbon intensive as the transportation sector, particularly when it comes to heat. So anything related to steel making, anything related to cement making has huge potential for decarbonization using power converters. And if you want to achieve this net zero by 2050, you have staggering numbers of power converters you need every year towards that goal. So you're talking of hundreds of gigawatts, if not terawatts, to achieve that. So it's becoming a huge business, and here control can help to increase the efficiency of the converters and to make best use of them. If you're interested, there's a little book I wrote a few years ago pretty much about these topics. And I have a long list of people to thank. I know I've forgotten many of them. Many of them have moved on, but I've been very privileged to work with many people who have actually driven along many of these topics. And I think this makes the whole quest much more interesting and enjoyable. So a big thank you. A big thank you for your attendance. And thanks for being here and interested in the topic. And I think we will have questions afterwards, maybe in the coffee break. Thank you.